Okay. Hello, good afternoon, everyone. So today we'll be discussing about bit about the AC microgrid part, means how to simulate the AC microgrid section, or then we will be discussing about some DC microgrid architecture, some inverter control techniques, and the further we will be going through some harmonic mitigation techniques that have been discussed in this week's course. So mainly the microgrid architecture that we were uh, discussing. So it consists of various like this the, so it consists of various renewable energy sources like solar, wind, battery banks, etc. So each and everything needs to be taken into consideration before uh, going with the before means the simulation parts should be validated before implementing them in a hardware scale. So for that purpose, this simulation, or rather we can say this simulation objective, needs to be fulfilled, and for that the microgrid modeling needs to be done. So basically what we need to do is microgrid modeling. This is from the from the lectures itself, that like you know, so accurate microgrid modeling needs to be performed. So if we can model the microgrid accurately, then we can analyze the results in a much better fashion. So that would give some beneficial outcome. So based on that, we can decide whether we would be implementing or whether it needs some updation or changes needs to be done, and whether the system is feasible or not. Okay, so this is the first part. Then we can validate. We have this RTDS, means the real-time digital simulator, as shown in the last class in the in the lectures itself. Uh, so we have seen that the real-time digital simulator, the main working is that it works on real-time basis. So when the timestamp is 1 second, suppose we are working on MATLAB or any other simulation platform, so that 1 second is not the same as that of the practical 1 second. So here in this case, so in RTDS validation, as entire thing is in the simulation has been done in software part, then it needs to be validated on real-time system. So this RTDS gives us the platform to validate, and for here the time stamping is exact 1 second as that of the real time. So that's the advantage of this RTDS. So where uh, we can observe this some of these behaviors, static behaviors, some dynamic assessment of these microgrids. Okay, so firstly, and also, like if someone models any kind of system, means we have this CHIL subsection, where it is also known as controller hardware in loop. So we have SIL software in loop, and we have controller hardware in loop. So in software in loop, we have the entire software part, it entire thing is been done in the MATLAB or any kind of software platform, Python, PSSC, anything. So this is only related to the software part. But if the entire thing needs to be validated, so suppose somebody is working on controller CHIL, means controller hardware in loop. So if the entire system control has to be done, control system modeling or controller modeling needs to be done. So the entire part that is run in software, that part, suppose the microgrid, that microgrid or the this, let us consider this microgrid structure. So this part is first in software, and the controller that is being devised or designed, that runs outside the entire platform, means RTDS or Opal RT. And this, it has some analog input, digital input, or analog output, digital output pins. So it communicates with the software part, and the controller that validates the working of this controller, working validation. So similar is that for the hardware validation, which is also called HIL, hardware in loop. So hardware in loop. So here also this entire hardware section, hardware, here the hardware was outside, only the controller was hardware was inside, means it was representing in the software domain. It was the analogous of that entire hardware setup. But in high hardware HIL, so the entire thing needs to be validated on hardware scale. So to validate in hardware scale, is HIL platforms developed. Okay, so there are two types of assessment that needs to be done: continuous real-time simulation, as given, or hardware in-loop testing, HIL testing. Okay, so that's the thing. That is the thing that I have discussed. Here, these analytical studies can be performed in faster, and offline simulation process can be done. Offline simulation programs can be done, and also, in real-time basis, here also the real-time simulator can operate in a similar manner to the real microgrid system. So it represents the real microgrid system as I've shown here. Means the entire part is within the software. This entire microgrid is represented in the software domain, and that assessment will be done. Suppose if you need the CHIL validation, then the CHIL section would be outside, and as it is. So the representation would be inside. And this is mainly from the software validation side. Now the hardware testing. So it has the capability of real-time simulators, which allows design and operation of microgrid control. So we can protection power devices. So we can validate whether this entire thing can actually perform well in the practical system or not. So that's the overall, means that's the aim or agenda of why this continuous real-time simulation needs to be done, and hardware in loop testing needs to be done. Okay, so before that, so for this microgrid, this is the AC microgrid case under study. So which what we can see is that here a is there PV is there, which is delivering zero point 0.4 megawatt. Here you have a diesel generator. Here we have a lithium ion battery. So this is the grid, which is 480 volt. So what we can observe is that this lithium ion battery, diesel generator, PV, each and everyone would participate in. This is the microgrid that has been framed to deliver, to cater this load. So each and every time the case study will be performed, means on the basis of that some results will be discussed. So here we have case number one, where in the case number one we can observe that that DER. So DER is absent and the grid is feeding. So grid is feeding the load. Okay. So accordingly, this is the generator, this is the PV, this is the diesel generator. So diesel generator has been kept to maintain the system balance, the frequency balances, or suppose if there is a fluctuation in the uh, generation because renewable sources are uncertain in nature. So last day also you have discussed that suppose we have such issues where uh, suppose there is a here it is a solar PV. Suppose there is a PV. This is the bus. Here is a PV. Here is a battery energy storage system. Let's suppose here is also wind. So etc. So each and excuse me, each of them is are feeding the load. Means okay. Let's just revert this direction. So here it is feeding. Here also it is feeding. And this battery energy storage system, it has the bidirectional feature. So what excuse me, so what it can do is that it can store the energy, and here it's the grid. So here suppose consider a breaker so that it can operate in both islanded uh, operation, so that in microgrid operation or grid connected mode of operation. So what it can do is that suppose here, and each of them needs to work on their MPTT, means this wind, PV, so that to extract the maximum power point, the converter should be operated so as to there it can have bidirectional means two converters like DC-DC and then DC-AC, or single converter, two converter system or single converter system. So it can have two converter system as well as single converter system. Again, when both of them are working on MPPT, suppose both of this wind has maximum power point during the night hours, whereas this solar has this maximum power will deliver this maximum power during the daytime. Now, what the BESS can do, it can store the energy because suppose the load that needs to be delivered, suppose this is a load. So this load is not means suppose let's consider that this load is around requirement of this load is X. So if this and this entire PV wind BESS that would be if we can accumulate the entire power generation means PV wind etc. So let's consider that to be Y. So if Y is greater than X, then what it can do wind and PV that it comprises to Y. So what it can do, it can charge the BESS, means it can store that much amount of energy in BESS. Now, during the night hours when there is absence of PV would generation would be zero, but means PV generation would be next to zero because in the night hours there is no daylight. So, but wind is there. So, due to this wind power, generation would be present. So, based on this wind power generation, this would also suppose in night hours also. Let's consider y is greater than x. So again, BESS would charge. Now there's a limitation, means the SOC limitation is there for this be battery energy storage system. This SOC cannot, the SOC limit has some maximum limitation as well as some minimum limitation. So beyond below which it cannot go down and above which it can't scale up. So when the SOC limit has reached its any of its reached its upper limit in this case, so that would inherently lead to and in such a condition also if the load is less again, if load has become more than generation, then BESS can deliver the power, but if the load is less, so again the condition, now we can't operate the entire system in MPPT. Okay, we can't operate this. So based on that, the pitch angle of uh, of the wind turbine has to be means it can't operate at MPPT. So for that we need to change the pitch angle to some other value so that it operates at lower power value. And similar is the for also the photovoltaic systems. So here are some of the challenges. So to analyze each and every challenges, so a large number of cases has been means it has been created means in software platform. So based on that, if we can analyze those cases and then we can get some results, and these results are validated in RTDS. So that would be like the entire system, entire microgrid. This microgrid that has been framed. This microgrid is has been framed here. So for this microgrid, we would get some various cases or various observations based on some cases. Okay. So let's consider for the grid connected mode. So first case where the DERs are absent. So we can observe that the the grid connected currents here it has some value, it possesses some value. We can see it has some value, okay, but others are nearing zero. It's minus 9 for example. So these are absent. So what we can see, the entire power is being fed to the load. So entire power is being fed to the load from the grid. Okay. So and this is a steady state mode of operation. So this is a steady state operation. Now coming to case 2. So here we can observe that now here we can see that all these currents, battery currents, these PV currents, generator currents, all are approximately their zero value, means 5 into 10 to the power minus 9. So they are at their zero value. So entire power is being fed from the grid side to the load. In the second case, we can see that there are no DER in the system. Okay, but there has been some load switching done at this point of time. So based on this load switching, these breaker currents, like this is the point of common coupling voltages and this is the point PCC breaker currents. So we can observe that there is some steady rise in the current. So this gives the dynamic behavior of how the changes would occur, and it again sets to another value. So this was previous operating condition. So this value changed up to a different level. So you can observe that here only just a load switching took place. Nothing else. Means the DERs are also DERs disconnected here also. And it is a grid connected mode of operation. Now in case 3, here the yes, here we can observe that the battery is switched on. We can observe that battery is switched on and it is delivering point 3 of that power, and the load power was point 0.5. So the remaining power, sorry, the battery was in charging mode. If the battery is less than 0, that means the battery is getting charged from the grid. So battery is getting charged from the grid, and PV is operating at MPPT, means the solar is working at MPPT, as well as this diesel generator. Diesel generator is also operating at the overexcited mode of operation, so that it can help in voltage regulation mode. And so it can allow, or like the diesel generator, it can operate, or it can help in voltage regulation. So here we can observe that the grid is feeding 0.42, and out of this 0.42, 0.3 is being taken by the battery itself, and PV is feeding zero point 0.4. So PV is feeding zero point 0.4. Here it is minus zero point 0.3. Here it is 0.42. So 4 and 4.82. So out of these 8, 2.53. So remaining 5.5 is being consumed by the load. So that's the overall scenario. And for that, we can observe that in each of these cases, the grid current, which was in this previous case, if we can observe that 0.85427, here the grid current got reduced. Here the grid current is, sorry, okay, not reduced, because the grid is also feeding the battery. So the we can observe this is also again a steady state operation with a grid current value from 1.809. So that's the, okay, there is another case 4. Yes, so here also DERs are switched on, means the PV, then the battery, and as well as the diesel generator. But here the battery is discharging mode. Here the battery was in charging mode. Again, here the battery is feeding zero point 0.3, PV is feeding zero point 0.2, diesel generator is there for voltage support. So zero point 0.3 and zero point 0.2, it is coming as zero point 0.5, and grid is feeding nearing to 0, 0.0267. Okay, so again the load power is zero point 0.5, load power requirement is zero point 0.5. So it is for voltage support. So, excuse me. So here are some of the grid connected mode of operation. Some cases where we can observe that each of excuse me, each of these system can operate in the grid connected mode. And now excuse me, coming to some isolated mode of operation where the system is uh, islanded. So here we can observe that the grid is being tripped. There is no connection from the grid side. Okay, so that's it. Here in case one, again, excuse me, battery is in charging mode and PV is operating at MPPT. Diesel generator, here diesel generator, both voltage and frequency support. Okay. So, so again we can observe that from the grid side, since it is disconnected, the grid side power, grid side current is zero, and the entire steady state operation, we can see that the battery, PV, and the generator and the diesel generator, both of them are feeding in a steady state mode of operation. And here also the diesel generator is zero point 0.4, PV is zero point 0.4, and battery is charging. So this is minus, and this load is also zero point 0.5 minus. So entire overall system is balanced. Now in case 2, here the battery is in discharging mode, so it is delivering power. So PV is operating at zero point 0.2, diesel is giving voltage support. So and load is consuming the zero point 0.5. So the power is being fed from the load side by this PV as well as the PV as well as the batteries to deliver to the load side. So okay, the last is here. The entire system is same as that of the previous one, only the switching action took place. Load switching took place. So at this point of time, this load switching took place. So for that, each of these system, a bit of unbalance occurred, and after that, the steady state currents we can observe. This is the final form, the transient part. There are some transients we can observe, and this is the final steady state value. But here also, the grid side power current reading is zero. This is the time that took for the load to change to a different value. Okay, so that is mainly the how AC microgrid simulation has been performed, so that a real-time overview can be tested in the RTDS platform. So the entire system, as we have discussed here, the entire validation has been done on RTDS. So next is the entire system that we have discussed, which was AC. Now the entire system has to be operated in DC. So as we have discussed previously, the need of DC microgrid. So we need to reduce the converter converters, reduce the converters or converting. That's the aim. And since the generation of PV, mostly as we can see, the generation of PV is more. So and the generation is in DC. So the converter stages only one converter. If we just need to use this DC-DC converter stage, so this converter stage would just uh, can be used, because if the loads are being fed, means that the load bus or the load bus is in DC, load bus is DC, then no need to convert again to DC to AC and then feed the grid side. So the converter stages gets reduced. So we can see that PV panels only one DC-DC converter is being used. Wind also, here only for the wind two stages required. Otherwise diesel generator, AC-DC converter, battery also DC-DC converter, supercapacitor DC-DC. So mostly single stage converter can be used for standalone DC microgrid system. And here mainly we can see that the PV panels, diesel generators, batteries. So like these are loads also, some loads are there, and wind needs to be just done from window from two converter stages. Here we can see. Otherwise, they can be fed from bidirectional uh, buck boost converters. This DC-DC side. Okay, so also if we need to make some interconnection between two local DC grids, so suppose this is DC microgrid 1 and DC microgrid 2. Here we have substations, PERs, loads, etc. Similar is the case here. We can use just bidirectional DC-DC converter to remote connect both of the systems. So the advantage of this system is that cost cost efficient. This entire system is efficient and reliable. Also, um, quality power can be maintained. RES security. So these are some of the means interconnection of the mode of interconnection of two local DC grids. So some impact means how this would aid means we are trying to minimize the cost. So mainly we need to reduce the economic aspects as well as from the power quality aspects. So best quality power needs to be delivered on the basis of minimum amount of cost to be invested. So some of these optimization problems that like the optimal DG placement problems, as we have discussed in 2 3 classes, 2 3 weeks ago. Is optimal um, like DG placement. So mainly this can be considered to be a cost minimization problem. Okay, the optimal DG placement side part. So here we can also see that this interconnection as shown in the above figure, the replicated version here it is that as simulated in the RTDS platform. So these are PV panels, storage systems like this is DC-DC converter. These are also the DC-DC converters, and since this is the DC bus, so the loads that needs to be fed are also DC. So this is for the microgrid 2, this is microgrid 1, and this is the bidirectional DC-DC converter that is interconnecting the two sides, means the two autonomous DC grids. So that is aiding the entire system to work in a better fashion. So we can see that since both of them are means location on basis, if we say see from the location basis, they are far apart, and here this battery system or the battery storage, the entire principle of this or the operation of each of these microgrids are uh, quite similar means suppose these microgrids are excess of power, so they can feed the other side means microgrid one. So this entire system, this is full edge bridge converter. So edge bridge converter. So the advantage of this system is that control action can be done. Suppose this controlling is automated, so controlling action won't require any kind of external uh, input. Means this can be automatic one. Or again, if we can see that the if suppose area 1 has excess, so it can deliver to area 2. Suppose in nowadays the EVs also play a vital role in, although here the EVs are not been discussed, but EVs also play a vital role because this V2G mode of operation, if on a stretch of time, if suppose people are having some amount of they are having some amount of uh, SOC value around 50 to 60%, so that 60% SOC, and they won't be staying for a long amount of time. So what they can do is that they can feed the each and each and every will suppose the MG1 microgrid 1, and during this time, so that would aid the entire system, but a dynamic condition. So vehicle like if suppose that amount of energy which is being fed from the EVs, that part, is not required from the uh, area 2 side, area 1 side. So what they can do, if area 2 needs some this network microgrid concept, this network microgrid concept is quite an evolving domain. So many people work in this domain. So mainly from the DC-DC side, this interconnection of these two local DC grids, as you can see, operation this keep this creates an ease in the entire system of operation. So that's the overall view of how to integrate these DC grids or how to simulate them first, and then we can try to implement on a hardware scale. So then we have some inverter control methods, inverter controlling techniques or challenges in parallel operation of inverters. So mainly to improve the generation capacity. So we need to what's the need of this parallel operation of inverters? So it's just to improve the generation capacity. So mainly this PV side or the wind side, both of these have some uh, parallelly operated inverters, and these inverter technologies, we can observe that the inverter 1 as well as inverter 2, both of them are feeding through this is the uh, grid side inductance. So we can see some interactive current and common current. So in this situation, suppose they are in parallel. So parallel connected inverters are ana- excuse me, analogous to current sources in parallel. So that's the overall objective of now. This is the single inverter along with the control system. So this is the grid side I21, that current I21 needs to be controlled. So this is a feedback. This I21 needs to be controlled. Excuse me. Here we have an LCL filter, LLC. So LCL filter is present. Then so if we can want to see the closed loop gain, so we can observe, excuse me, we can see that the closed loop gain, this is G01 and I21. So this is the closed loop gain. Now, now for the parallel inverters with their control system in operation. So here the question was for parallel, excuse me, parallel operation of the inverters. So excuse me. So sorry, excuse me. So this is for the two parallel inverters. The transfer matrix. So for the interactive mode of operation, the final the interactive current is of the form. Common current. So based on that, for stable operation, this interactive current as well as the common current, both of them not have poles on the right half. So as we all know that if we have poles on the right hand side of the plane, that means that the system becomes stable. Sorry, unstable. That means if we all the poles should be, if it is on the j omega axis, then the system is marginally stable. And since we need to operate on a stable mode of operation, so all the poles should be on the left hand side, and right hand side it is unstable. Okay. So both these interactive current as well as the common current, they need to share the this interactive as well as the common current stability should be ensured for the parallel operation of the inverters. Okay. Again, the based on the filter properties, we have various based on filter properties. These two currents can be different. So, in ideal operating case, the filters filters should have the same should possess the uh, same type or should possess the same features or properties. But in practical operating case, this might differ. So if this process differs, but still we need to deliver the best possible outcome so that the inverter operation can be done. Parallel operation, parallel operations can be assured if both these in parallel filters like the parallel inverters, if both of them have the same inverters or same filters, but that's not the case in practical scenario. So there are some deviations. So to maintain the system to be in a stable condition, all these features needs to be addressed. So this is with mainly with the parallel operation of the inverters. And now coming to some power quality mitigation techniques. So in the transmission side, what we also know that the uh, power quality improvement needs to be done, and this power quality improvement can be done from like fax devices, flexible AC transmission system, fax. So these fax devices enriches the power quality. Like suppose we need to improve the power factor or the voltage compensation, mainly compensation techniques. So for that we use various kinds of passive filters like shunt filters, series filter, hybrid filters. So series active filters, now this is unified power quality controller. This is DStatCom, both shunt and series mode of operation. UPQC, shunt active filters, they are connected in parallel. The series active filters, this part is connected in series. So that's the series. So current mainly by improving the uh, series active filters. So the current procedure improvement can be done, and using the shunt active filters, the uh, yes, using the shunt active filters, the shunt compensation uh, can be done for the voltage. So by improving both voltage improvement and current improvement, ultimately power power improvement can be done. So here the main motivation is to improve the system harmonics or harmonic mitigation techniques. So that's the overall aim, that is harmonic mitigation, because with the increase in harmonics the system power losses also increases, so that thing needs to be taken into consideration. So what we can observe is that here, okay, let's because here it is some results, but before that, to understand is the cause of harmonics that can be introduced in the system. So uneven switching can also switching, then nonlinear operation, AC or DC drives. So what are these of these systems may lead to uh, harmonics in the system, and this harmonic needs to be mitigated, and based of their uh, cause of these harmonics, due to the cause of these harmonics, some production of some harmonic currents, harmonic currents, so it can affect transformers. Transformers at large means mostly transformers as well as the motors, etc. And it may also cause, as also discussed, that the current increases due to the presence of harmonics. The RMS value of that curve, the current increases due to the presence of higher order harmonics, and based on that, the overloading occurs, which subsequently can also lead to overheating, and that's the overall operation of what's the cause and of harmonics in the system and why it needs to be mitigated. Because now in the microgrid system, so if we have system harmonics with in place, so for that the regular operation of the devices which are uh, prepared, which are working on the fundamental frequency, which are designed to work on the fundamental frequency, that system or that equipments would on those equipments it would be some issues would be imposed, and based on that these are the issues like overloading and the harmonic currents injection. So overall the system would face some operational challenges. So for that, some a compensation technique. This is the experimental experimental setup. This is the setup where we can see that this is the utility grid. This is the nonlinear loads. These are the nonlinear loads, and these are PV arrays, batteries, wind, and these are the DC-DC boost converter, DC-DC bidirectional converter, and this is a boost converter, DC-DC boost converter. There are some DC loads connected, and these are the controllers. So based on those controllers, this was what I was saying in the first part also, that this FPGA, this is FPGA, this is controller outside, means that CHIL part. This is the controller which is outside. This entire system, this entire system is in within the software platform like the RTTS. So this software needs to be this is the controller and this is the software section, and based on that this is the nonlinear load side. So here the assessment has been done that with compensation and without compensation. So this is the uh, series this is the shunt compensation unit and series compensation unit. So what we can see is that suppose this is the voltage waveform, this is the voltage waveform blue one, and this violet pink one is the current waveform. So if the system is without compensation, then the receiving end side, what we can see that the currents and the voltages are imposed with some harmonics. Okay, so using this, but the requirement is sinusoidal operation. So for that, this compensation needs to be done, and this compensation as devised from this controller, the CHIL mode of operation, controller hardware in loop. This controller would observe these harmonic changes in the waveforms, and based on that, the AC waveform has been observed. This is the AC waveform, and the improvement in the profile is ISA as we can observe, and VIA. So we can observe that there is a significant improvement in the load profile, and this is from the CRO outputs. So or DSO. So that validates that the system, if we use the system with some compensating units in the system, so that would inherently improve the system performance, or it can mitigate the harmonics in the system, right? So that's the overall discussion of this thing. So today some questions I have taken out. So these are questions, the assignment questions are not. So I prepared some questions from some different assignments. So I'll just write them down one by one so that you can. So Parkes transformation yes, this part. So the Parkes transformation is used to transfer from a alpha beta 0 to ABC reference frame, then DQ0 to ABC reference frame, then ABC to alpha beta 0 reference frame, and ABC to DQ0 reference frame. I think it's visible, right?
Option C, sir.
Option C. Option C is ABC to DQ0. ABC to alpha beta 0. No, no, this is not option C. Not option C. Something else. Okay, by that time, we'll move to second question. Energy management. DC output. energy storage system. Extract maximum
Option B, sir.
option. Okay, for this first one, if anybody uh, is willing to answer, otherwise, uh, first one, any final choice? Yes. Parts transformation and also in synchronous generators. I think in most probably you have studied in machine. Uh, if any of you are from electrical background, then parts transformation is been generally taught in uh, synchronous generator modeling, power system dynamics. So okay, so this answer would be D, ABC2. ABC2, DQ0 reference. Okay, this one, energy management strategies in DC microgrid aim to increase the stress on energy storage system, reduce peak energy deficit, degrade the lifespan of energy storage, extract maximum power from PV and wind. Excuse me. Okay, any answers from your side? Excuse me. Energy management strategies in
B is
different.
the answer. B.
Yes, B is the answer. Yes, B is the answer. Okay. Which stability involves response? Small disturbances. Yes, we are thinking. So, which stability involves the response to small disturbances that occurs in microgrids producing oscillations. So A is steady state stability, B is transient stability,
A, sir. Option A.
dynamic stability,
Steady, that small transient. I think it is a transient.
small
Small
dis-
disturbance is transient only or dynamic. Either transient or dynamic.
yes, so but only one answer is correct. So
Dynamic will be, sir, because it is oscillation. Dynamic stability.
yes, dynamic stability is the right. Dynamic stability is the right answer.
Why not? Why not transient?
So transient stability is similar to if we consider the small disturbances, it is a continuous process. When the disturbances occurs, like the transient stability that I have discussed, is mainly during the load changes. So just a transient phenomena when the load gets shifted from one suppose the loading scenario just changes. So for that loading scenario change, the the operating point gets shifted to another operating point. So during that intermediate time frame when the change is occurring, that is referred to as the transient stability. But here the small disturbances, that is a continuous process. So the transient, or that is producing oscillations. So these oscillations producing the small disturbance producing oscillations are mainly referring to the dynamic stability. Means this is a continuous process, prolonged time interval. Okay. So transient is just between switching.
Sir, for transient, it is actually large disturbance, means
Yes,
that,
yes, 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 yes,
and
right.
that not produce oscillation that die out at the
Yes,
last.
yes, 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 yes.
And
Damping.
sir, for this small disturbance, if there was no oscillation, then it would be steady state.
Hmm. Yes.
If a small disturbance and die out, then it is a steady state stability.
Yes. 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 But if this process is continuous, then it is
And produce oscillation, then dynamic.
dynamic stability. Yes.
Yes, sir.
Thank you. Thank you. Then we have yes. Excuse me. So identify the incorrect statement. Then you need to identify the incorrect one. Okay.
C is the incorrect one.
Inductive filters, orthogonal distribution static compensators, inductive filters. Yes, voltage regulators. Work only voltage rated. Excuse me. Yes, P is the correct answer. UQFC. UPQC, sorry, Unified Power Quality Controller can overcome only voltage related power quality problems. Yes. Okay. No. Excuse me.
All are correct.
Yes, yes, a solar inverter can act as a statecom. Battery integrated to solar wind energy conversion system through a bidirectional converter will start charging when DC voltage is raising. Yes, this is also correct. Again, when it is discharging when the voltage is dropping. So all options are correct.
See,
No. Similar to inverter system with similar inverters, if current control loop are equal, if both the current control loops are equal, the interactive currents occurs when if this current control loops means since the LCL filters are not the same in both means it can't be designed accurately in the ideal condition it should be same but in practical operating scenario it can't be same so due to which this interactive currents exist so if the entire system is similar means if it is the ideal case then what would exist that's the question.
so what is the this interactive current?
The interactive current is suppose this question is in the parallel operation of inverters. So the both inverters should work in means if they are to work in parallel. The both configuration of suppose this is one inverter, this current control loop, and this is another one. Both of them needs to feed the grid because suppose this one is from the solar, this is from the wind. Okay, or any other solar units, but if they are to feed the grid at the same point PCC, same PCC, for that the interactive current exists when there's a difference between the IREF and what is IREF. The IREF one is the reference current. Reference current. Suppose here you can observe IREF. This is the reference current means the current which is flowing on the means I21 is the operating current. Okay, this is the feedback. I21 this is the feedback. Let's consider for the single area mode of operation or single inverter mode of operation. Then it will be easy to understand. So this is the current. Okay, this is the feedback point, and this I21 is the current that needs to be controlled. So this I21 is given as feedback. Now, this is the control plus minus gain that we also all know that sum are block or uh, here plus and positive and negative. So this is the reference set point value, and this is the reference set point value for suppose converter 1, and this is again for converter 2. And these two reference set point values should be somehow similar so that if both of them are similar then only they would be feeding the PCC at the same uh, voltage means the same current I21. This I21 would be fed in the same manner with the operating L and C, this LCL filter, provided that these LCL filters are ideal. And in these ideal conditions, if both of them are similar, then interactive current, the existence of this interactive current would vanish. So this is the what is called the interactive current. This is the transfer matrix where the G, this is the uh, closed loop gain that we have observed, and this is the interactive current. So when both of them reference are same and they can be same when these filter designs are perfect. So pertaining to these conditions this interactive current exists, and this is what was the question that uh, uh, yes. So if two inverters are same, similar inverters, the current control loop are equal, both the current control loop are equal, then only which current would be present. So current control loop gain are same. So if loop are same, then loop gain is same. So if there is a similar loop gain, I ref value is same. Similar inverters, so LCL parameters are also same. So in such a condition, which option would be correct? Interactive current exists, common current exists, harmonics will exist, some same harmonics, some harmonics will exist, and none of the above.
Oh, sir, both A and B will answer.
No, no, no. As just I've told, no, that key, if both of them are similar, then this IREF 1, IREF 2, they would be similar, and also the gain, that GPD value 1 by 1 plus GP, GP, yes, GPD by 1 plus GPD. So these all values are same. So this value is 1 and this side is 0. So existence of interactive current is 0. So only the common currents would exist in this scenario. Only common currents exist. Interactive current, presence of this interactive current is zero, no interactive current, because it's the ideal operating case. So that won't be quite feasible in the practical domain, but this is the ideal operating case. And if the system is, if this is the system in ideal case, so the interactive current won't exist, only the common currents would exist. Okay.
But in practical, both current will exist.
Yes, yes, yes. In practical case, both current would exist. In the practical operational scenario, minus and microgrids, in a practical microgrid operational scenario, both of these can't be same. Both the LCL filters can't be same, because no one can design the accurate or exact same or similar. Means they would try to design, but can't be same in practical operating scenario. So that would inherently lead to some issues, means challenges where.
Can we say this interactive current is a current which is flowing in the system, not going to the load?
Uh, it can be considered as a current which is flowing from one inverter to the other. Means if there is a, suppose there is a AC loop, this is the sinusoidal wave for one inverter, and this is for the other inverter which is a bit displaced. Okay, so if we this can, if we us so if you can say that this much is the phase displacement between these two. uh, this is for inverter 1, this is for inverter 2. Okay, so this much about the phase displacement would, because when it has a peak, it doesn't have a peak, so it is mm, a bit deviated from the peak. So this much of deviation would lead to a circulating current that would flow from one inverter to other inverter. So that's the interactive current. Means when parallel operation means similar, this is the similar case when the, what is the need of these synchronous generators play working in parallel operation of synchronous generator. It's a similar fashion, means the parallel operation of inverters. If both of them can't synchronize at the same point of time, if both of them have a, if just take an analogous example of synchronous generator, if both these synchronous generators don't have if both of them are operating at 50 hertz, but if suppose this is 50.1 hertz and this is 50.05 hertz, so there is a phase displacement, there is a change in frequency. Okay, so due to this change in frequency, a circulating current will flow from one generator to other generator during the, that would be very minimum value. The same phenomena is here. This is the interactive current that flows from one inverter to another, or you can rather say that what you have also stated, that it is the current that flows within the system. So it's quite same. You can consider the same case. Okay.
But then this internal current will also induce some harmonics.
Yes, it is the effect of harmonics. Yes, it is a part of this harmonics. Due to the, for that only we need to use some compensation devices. That last module, that power quality improvement. So this was the module, or this was from the fourth lecture. So where the harmonics were discussed, and after that harmonics, how to mitigate those harmonics were discussed in lecture 5, means in this week's session. Okay. So it was this session was mainly what can be the possible harmonics that can arise in the microgrid scenario. Means we can use various kinds of AC loads. We can switch on, we can switch off this AC loads, loads, etc. So how they would affect the operating equipments in the system, and based on that, how to mitigate those mitigate those harmonics that were discussed in the next module, like the shunt statcom, or the series compensators, shunt compensators, UPQC. Okay, so this would raise harmonics. This is the cause of harmonics. Okay, I think it's okay. Okay,
Okay, okay, okay.
okay, okay. Thank you. Okay, some two more questions. Hybrid system. um,
B supercapacitor.
yes, yes. Here you need to find out the
C is the answer. C.
C operating point of the potential of power drawn from the PV array decreases. Yes, C is the answer. Move away from NPT. Okay, then okay, let's wind up the session here today. If you have any kind of queries, then ask. We'll wind up the session today. We'll meet on the next Saturday. I think you're fine with these questions. So if you have any questions, you can ask, or if you don't have, then we can uh, wind up the session today. It's up to you.
Sir, please share the previous slide of questions, sir.
Yes, I have shared. I want
Means just last question.
yes, yes, last.
Last question, sir, of the quiz.
Okay, okay, last question.
Operating point move away from it. So, sir, MPP is the maximum point of IP and VP. From
Yes,
that,
yes,
operating point will move away. Then it will decrease.
yes. Move away.
Means, sir, it will be below VOC IOC curve or above.
Yes, this one is the curve. This is the MPP. So it would move away. Means if there is a if the system is operating at MPP,
Move away. Okay, sir. Yes, yes. Thank you.
thank you. Okay then. Okay then.
Okay, sir. Thank you.
Thank you. Okay, let's.
Thank
Yes, welcome.